Could you please introduce yourself?
Oh, yeah, I'm Karin. I am a marine scientist that works on coastal problems and do a lot of numerical modeling and increasingly a little bit more data science. So this talk is actually Zhang Xiao's work. He's my PhD student, and I wouldn't let him come because he needs to finish his PhD in November. So he's a bit disappointed, but hopefully I'll do justice to it. One of our challenges in New Zealand is that we have a lot of low-lying land in our coastal areas, and that low-lying land is often fringed by wetlands and mangroves, though a lot of those wetlands have been drained for farming. So those are easily inundated with sea level rise. And so one of our challenges across a number of different programs is to understand what the fate of those will be with sea level rise. Okay, and why are we so interested in these low-lying areas? Well, first of all, there's a large amount of carbon sequestered in these coastal low-lying areas. They're organic, rich soils. Those intertidal and wetland regions are at the base of estuarine food webs. So the food baskets of New Zealand coastal environment are in there. A lot of the shellfish that we collect is from our estuaries. The low-lying land is, of course, great for farming because those soils are really nutrient rich. And so a lot of our most productive dairy farms in the Waikato and Bay of Plenty, in Northland, actually in Southland, all around the country are there. They're very susceptible to flooding, as I said. And so their general future will depend on whether those wetland areas can migrate or not. And a lot of them can't migrate at the moment because they've got seawalls backing the back to protect the farmland behind. So at the moment, a lot of our modeling for our wetland region is based on very, very simple models. And those models are often based on what we call bathtub predictions, which basically we just rise the sea level using a contour map, and then we get the new contour. And as you can see here, this is the Hauraki Plains with Thames, and you can see a lot of that will get inundated with sea level rise if we don't protect it properly. And so the models tend to work like this. They basically take the tide goes into the wetland, it drops all the sediment out of it into the wetland, and the emptied tide goes back out. And so they're very dependent on the shape of the tide, whether the incoming and outgoing tidal currents are the same size, because in reality, they're not. Whether those tidal currents are attenuated as you get into the marsh. And of course they are, because the marsh is quite high friction environment. So it takes a lot of energy out of the tide. And also whether that marsh has got channels draining out of it. And so that really complicates it. But what I'm interested in today is the sediment supply. So at the moment, we assume that the sediment supply on the seaward side of the marsh is just a constant number. And so, of course, that's hugely important because that determines how much sediment is going to dump out in each tidal cycle and whether that wetland will be able to keep its elevation up with pace with sea level rise. And so there's a big argument going on in the field saying, yeah, that's all right. The wetlands will be fine because they accrete sediment so quickly that they'll catch up. And then the other side is like, no, they're going to drown and we need to worry about that. So the sediment supply. Okay, so just to give you an idea, so the incoming currents can attenuate and they drop out the sediment as the power of the tidal currents reduces. And then the outgoing tides bring that sediment back on shore. So it's a really careful balance. Okay, so now we can do much, much better with our numerical modeling. We can use our state-of-the-art, very highly resolved hydrodynamic models like Delft 3D or ROMS. There's a bunch of different ones available, but it's really slow and labor intensive. And so the challenge that Zhang Xiao was trying to address with this chapter of his thesis is, can we use the remote sensing data that we have, machine learning, and the numerical models that we already have to make it all much, much faster. Okay, so that's our challenge. So this is work that was funded in part by the Bay of Plenty Regional Council, and they're interested in suspended sediment and sediment accumulation in Ōhiwa Harbour, just to the south of here. So this is a picture of Ōhiwa Harbour, and there's our instruments ready. And we've gone out and put out these instruments at those sites 1 to sites 5. And then our model has all the freshwater input into the harbor along those pink points and the tides coming in the outside. So that's our model. That's the numerical modeling grid up at the top. So it's really quite a complex harbor. There's lots of little channels and areas and bays and things like that. Okay, so what do we do? So we run the model. The model produces the tidal currents. It then takes the suspended sediment coming from the outside, suspended off the seabed, and on all these input points, and then it moves it around the harbor and then accumulates it. Of course, it has a number of parameters that need to be tuned in the model, right? A hydrodynamic model basically has the roughness that you need to tune, the amount of eddies in the model, but a sediment model has an order of magnitude more parameters that need to be tuned. And so we do that by calibrating the model. The sediment model, we actually take in situ sediment samples and we put them in a big tub and we spin it around and we get the sensor and we calibrate it. And there are these metrics that you have in engineering that you have to achieve, like Briley skill scores and things like that. Quite easy to do for the hydrodynamics. That green means we're in the excellent category, so that's okay, no problem. Very, very hard to do for the suspended sediment. Okay. And so here, this gives you an idea of what the modeling results might be, where you've got really fine sediments around the harbor and where you have channels where the currents are higher. The suspended sediment concentration is really high. This is averaged over a month of modeling time. And then, of course, the suspended sediment fluxes, which way the sediments go, would look a little bit like this. So up here, the sediments tend to move landward. And out here near the entrance, the sediments tend to move seaward, and these are null points. Okay, so the problem is this shows you the suspended sediment calibration. And we spent probably 3 months rerunning the model. Each model run takes about 2.5 days, right? And we tried all the different parameters. We don't have very long data sets, only about a month. And the suspended sediments are extremely episodic. If you have a wind event, it picks up sediments into the estuary. And so it's very dependent on the time of the year. Okay, this is where Varvara came in. And so we said, we're going to talk to Varvara. She's pretty clever. She's down at Canterbury and she's working on this program. What do you think? Can we use some of your cool GNN modeling that you've been doing with Ding's project? Will that work? And she said, well, you can keep going, working through your parameter space, but why don't you use your model and your data to train a machine learning model instead? And so that becomes a shortcut. So instead of trying to get the perfect parameter space, we'll just make a corrector and we'll correct the model. And then we can use the model for more and more. So given that we only have a month's worth of data, we decided to use the satellite data because there's now 3.5 years of Sentinel-2 data, and we have a number. So that gives us many more conditions that we can do. And so the first thing we did was to calibrate the Sentinel-2 data with in situ data that's collected by the council, Bay of Plenty Regional Council, to get a conversion. So our satellite data becomes our one source of truth. We're going to assume that that's the correct. And then what we did was we took our numerical model and we took our satellite data, both spatially resolved. And the first thing we did was classify that into regions. Okay, so we used, or Zheng Xiao used k-means classification, and he classified the root mean square of the model results between the model results and the satellite derived area. And so that's what he got. He did it separately for flooding currents and ebbing currents because they can be quite different. Ebbing currents brings the fresh water that's just coming out of all those rivers through the estuary, whereas the flooding currents bring all that open ocean water into the estuary. So we first of all decided it would be better to do it that way. And you can see that the channel regions tended to be one class. We allowed 4 classes. These in-between regions, class 2, and these higher regions in the estuary, which tend to be muddy, they tended to be class 4, whereas which one? Oh dear, I'm getting mixed up between flooding and ebbing. I think this is ebbing and that's flooding. And so you can see that we had one extra class in one of them. All right. And then once we got our classes, we then created a classification predictor regression model based on each of those classes separately. So we made 7 different models, and so we classified each of those areas and had a separate regression model for each of those 7 areas. Okay, so this shows some of the results for each of the classes for the ebbing model. And then, and then each of those classes for the flooding model. And so you can see the classes behave very different. Class 1 tends to have quite small suspended sediments, class 2 medium, and class 3 quite high suspended sediments. All right. And then we put all our classes together, one for ebbing and one for flooding. And you can see that's all the classes for ebbing and all the classes for flooding. Here's the observed suspended sediment concentrations from satellite. Here's the predicted suspended sediment concentrations from our regression model. And these are the testing data sets here. And then finally, that's everything put together. All right. And that's the numerical modeling results before and after correction. So the last thing I wanted Zhang Xiao to do is to tell me, did it make a big difference? If I was to understand the change in a wetland using my numerical model and the change in the wetland using my new regression model, does it make a difference? And so I got him to take all those data from all those spatial points and just look at the distribution of that data. And you can see that the Delft data predicts a very, very narrow range of variability, whereas our corrected model is much, much wider. So it's capturing all those really episodic regions, episodic events, and high regions of the harbor. And then the final thing, I think I'm probably running out of time, is to understand if we were to model the amount of accumulation in a little wetland in the side of the harbor using our old method and using the new method, would it make a difference to the accumulation? So this is the amount of accumulation using the new model, and this is the amount of accumulation using the old model. And so you can see that the difference between the sediment accreted in that area, in that wetland area, is actually an order of magnitude larger. So it could make a really big difference. The advantage of this is everyone around the world can get Sentinel-2 data easily. And so you can upscale to many different sites and estuaries around New Zealand and around the world using such a calibrated model to tune your actual model. So I think it's got good potential, and that's it. Questions? Yeah.
Thank you.
Yep, I had some conclusions.
Thank you. A quick question. Yep, right. No.
Well, okay. So the fact that it's really, really poor is because I didn't spend more time to make it better. It's not an indication. So the sediment model in Delft, you can have like layers of sediment in the seabed, and then you can also spatially vary the sediment in a hugely detailed way if you wish. The problem is we don't know what to put in it, right? So it becomes this infinite guessing game that goes on and on and on. But if you had really good data, you could make Delft really good as well. It's not a problem with the model. Yeah.
Another quick question. Yes.
Yeah.
Well, the last graph you showed, do you have the ground truths? I mean, there's a difference between the old method and the ground.
So everything in the new method is relative. It's the satellite data is the ground truth, and the satellite data has been ground truth to the council suspended sediment values at the sites. So it's not strong, but it has been ground truthed.
So like, I mean, like with the side where like there's a gray and a red eyes. So like, do we know which one would be more correct?
Yeah, I would take the red line, the one that's been corrected to the satellite data. But you're right. If we could go to a site where we actually had real accumulation data to test it with, that would be really sensible. There are some, the Firth of Thames has a whole array of sediment accumulation sensors that we could move to there. And most places are data poor, unfortunately.
Very good. Yes, because it's the end, and yeah, and you owe me a favor, so Eb especially.
So I'm allowed a question. What are the inputs to the boosted regression tree? I didn't quite catch that.
So the boosted regression tree is based on the root mean square between the numerical model and the satellite data. So that's used to correct the numerical model data so that it replicates the satellite data.
What are the input variables? What are the independent variables? What is the prediction of the error based on? Maybe the question is stupid, but
just
normally with the regression model, you have some independent variables and then you have the dependent variable.
I think his independent variable is the numerical model data, I think.
Good. I will take that for yes. Thank you very much, Karin.